Hey everyone, welcome to the, I believe, ninth miniKanren Uncourse Hangout. We've been talking about miniKanren implementation recently. We talked about unification, substitution, so that's a good thing. Talked about disequality constraints last time. Went into quite a bit of detail about that. And today we I guess can continue going and maybe talk a little bit about what a goal is, what a goal constructor is, all those sorts of things. So just keep trucking. All right. And Daniel says he's got around to implementing a first pass at a relational elementary cellular automaton simulator. Whoa. Okay, that sounds shiny. Would you like to show that off during the Hangout today? Maybe. Okay. Well, think about it. Either this time or another time if you want to show it off. Great. If not, no pressure. But if you want, I can also add that link to the Hangout. And a wild Ambrose appears. Hello. All right. And Orchid had a go at adding disequality constraints to miniKanren. Cool. I'd like to see that. I'd very much like to see that. We learned last time if you do equal/equal in chat, it turns up as a sideways brownie face or whatever, equal sign. So I guess not bang equals maybe is easier to read in chat. Yeah. Yeah, so it'd be interesting. Okay, so this is what I'm talking about, right? Like this is my whole goal, is that get to the point where people are starting to implement their own miniKanren-y or logic programming things to show off. So that's cool. It means that I can stop talking soon. Okay, but we will keep going through at least the micro miniKanren-y implementation stuff, and then we can see which direction people want to go with the Hangouts. But yeah, I'd very much like to see the miniKanren with disequality constraints, either on air if you want to show that off, or you can take that offline. Very cool. Nice to hear that. And I know there are a couple other people doing miniKanren-y projects. So yeah, Igor's got a logic puzzle in case anyone's interested. Okay. Wow. I forgot. Do we even have a mailing list? I was thinking, we should really have a mailing list for us to talk about this. Hey, Ambrose. So I don't know if we have a mailing list or not. If not, we should. Yeah, other than the miniKanren mailing list, I mean, I'm sure people will be interested in regular miniKanren mailing list also, but I'm thinking about just in terms of projects that we might want to do ourselves in communication, sort of just like playing around and stuff. But obviously, all those things I think would be of interest to the regular miniKanren list. So if you want to post those, that'd be cool. Anyway, I guess if there isn't a mailing list, I'll probably start one for the Hangouts, just because some of the things we talk about may not be of interest to the general mailing list, but it may be higher volume or something like that, or people might be playing around with systems that aren't quite tweaked yet, and then later they'll share them with the regular mailing list. Okay, very cool. Glad to see that people are hacking on stuff. Let's see. Yeah, I think we've got about a full house also. Okay, yeah. All right, well, I'll set up a mailing list then for sure. Yeah, good, Ambrose. Yeah, Michael Adams and I are working on some new cool miniKanren stuff that we want to get working, be able to show off. That's some grammar-based runtime type tree constraints and stuff like that. So, yeah, a lot of miniKanren action hacking experimentation going on in Utah right now. So it's very cool. All right, good. Glad to see people are getting to know each other and all that. What's do some miniKanrening. Let me bring up my Emacs. There we go. Okay. So I've just got this running transcript from the last couple of Hangouts, so it's got a lot of stuff in it. Now it's 500 lines long. But if you remember a couple of weeks ago, we started talking about sort of the simplified language you could have with just conjunction, disjunction, binary disjunction, binary conjunction, what that might look like. We started talking about equal and unification, and the notion of separating the introduction of a fresh variable from conjunction, the concept of conjunction. So trying to boil down miniKanren into a very simplified language, and we ended up with something like this, right? Where we're doing an and or conjunction of two unifications, but now our conjunction is binary. If we want to do a conjunction of three things, then we need to make two calls to conj, that kind of thing. And also, instead of having fresh that introduces a fresh variable, now we're going to make a logic variable using some sort of helper, and then pass in that logic variable to just a function. And basically, we're using lambda, which is Scheme's binding operator, to do binding of the logic variable. So this is one way to get around from having to have special syntax or macros or whatever. Okay, so you get this very elementary language for expressing computations like miniKanren. Okay? Any sort of logic programming language. You could do something like Prolog in the syntax also. Okay. So we were talking about, first of all, how you could boil down a regular miniKanren program into syntax, or sort of remove the syntax and make it this very simplified elementary form of logic program. We also spent a lot of time talking about substitutions and what it meant to walk a variable or a value in a substitution, right? How you look it up and how a substitution looks like an association list. It is an association list, but it looks like an environment in an interpreter, right? But one difference between an interpreter and a regular, an environment and a regular interpreter, the difference between a substitution and an environment is that in a substitution, you can have a logic variable on the left-hand side, and you can have logic variables on the right-hand side. So you can have a logic variable bound to a logic variable, or a logic variable bound to a list or data structure that contains a logic variable. Whereas in an environment, you have a variable that is associated with some value, some just ground list or something like that. No, you're not allowed to have variables on the right-hand side. So that's one distinction between a substitution and an environment, is that in a substitution we're allowed to have variables on the right-hand side. In the substitutions that miniKanren uses, these triangular representation of substitutions, there are some additional restrictions that we have. One rule is that a variable only appears once on the left-hand side binding. Okay, so if you have y.6, in the rest of the substitution you'll never have y on the left-hand side. Okay, you can only have one binding of y at a time. And so there's some other properties like that we rely on. And also, probably the most important thing to know about our representation of substitutions is they're triangular, is the technical term. But what that means is if you want to know what the value of y is in a substitution, okay, you can just look it up, like in a substitution, an environment, just do a regular lookup in an association list. You'll find that y is on the left-hand side of this pair, so therefore y is bound to 6, so therefore y walks to 6. If you want to look up the value of x, though, it becomes a little more complicated, because when you are walking down the substitution, that association list, you find that x isn't bound to 6 directly, but instead it's bound to y, which is a logic variable. Once you find that y is a logic variable, then you have to walk y in the substitution. right? So you have to start over again with this new variable. And as we can see from the top example, y will walk to 6. So walking x will also lead to 6, but it has this extra level of indirection. So x has to go to y, and then you look up y. And you could have a long chain of these variables, and that could lead to quadratic cost, so like n squared costs, and looking up a variable in a substitution in the worst case. And we also talked about how different representations of substitutions can get around that, maybe using some smart, non-destructive union find operations, or stuff like that. Might be able to improve things. So that's a cool area to explore. So we looked at that. We looked at what lookup would mean, and looking up a variable and all that sort of thing. So I talked a lot about triangular substitutions and how they differ from idempotent substitutions, which are sort of the more mathematical version of things. In idempotent substitution, you have, if a variable is appearing on the right-hand side, it's never going to be on the left-hand side. Basically, you can apply the substitution to a term, and then apply the substitution to the resulting term, and you get the same value back. Okay, that's why it's idempotent. It's the mathematical term. All right, so we spent a lot of time talking about substitutions. Spent time talking about this walk operator, okay, which is basically how you look up a term or a variable in a substitution, find its value. We have a definition of walk. We had a couple definitions of walk, okay. And this last definition of walk here is the definition that you would see in miniKanren, okay. And I actually I grabbed from Jason's GitHub repo the miniKanren code. Okay, and the miniKanren code is very short. It's only 51 lines. But you can see that this definition of walk matches the definition of walk we had from, I think it was 2 weeks ago. Okay, or 2 or 3 weeks ago. It was a while ago now. Okay, so this is the definition of walk you have in miniKanren. We talked about extending a substitution, right? If you want to say that U is bound to V and extend the substitution S with that binding, basically you're just consing on a new pair of U.V to build up the association list. And this would be very similar to extending an environment, basically, in an interpreter. Okay, and then we started talking about unification and how you would unify two terms with respect to some substitution. We went through all the cases there and so forth. And this version of unification looks very familiar to me. This looks, once again, let's look at the miniKanren code. I believe this is pretty much the same. Yeah, so if I just this up on the same line, and if I made my square parens round, then they look the same to me. Yeah, so basically we've got, we're starting to get part of miniKanren build up. We have definition of unify, we have definition of extending a substitution, all those sorts of things, definition of walk. So as we're going on, we're building up more and more of the miniKanren system. And then last time we talked about disequality constraints, or this not equal or whatever. And that allows you to say that two terms are not the same. They don't have the same value. We talked about what that meant. We talked about how to implement the disequality constraints in terms of unification, right? And that was the kind of the fun part, is that you can implement disequality constraints in terms of unification in a very nice, clean way where you look at the value returned, the substitution you get back from making a call to unify. There are basically 3 different cases, right? So, and we talked about the cases here. Cases 1, 2, and 3. You either get back hash f, representing failure of U to V to unify in S. You get back the original substitution, or you get back an extended substitution. And the same thing happens when you're trying to solve the disequality constraints. You have 3 cases, the same 3 cases from unification. It's just that you interpret those to mean different things. So that's really cool. I thought that was really neat that you can implement disequality constraints using unification. And that's why once you understand how unification works and how microKanren or miniKanren works, it's not that hard to add disequality constraints. Okay, so those are all things we've talked about. And we also talked about other types of constraints and having not just a substitution, but a constraint store that gets passed around and all those sorts of data structures. Okay? So that's just a quick recap. And now we're going to kind of keep moving on. One thing I wanted to point out, if I hadn't already, is that last time we talked about unification, disunification, and so unification gives you this equal operator as the basis for equal in miniKanren, and disunification is the basis for equal/equal, right? Saying two terms aren't the same. It turns out that those two constraints, sort of equality and disequality constraints, if you will, over trees, tree terms, which is what we end up with in miniKanren, those form the basis of constraint logic programming over trees, CLP tree. Okay, so this is a form of constraint logic programming over trees, tree terms, when you have these two operators, equal and the disequality constraint operator. So if you ever wondered what constraint logic programming or constraint logic programming over domain X is, you can have different sorts of domains, but to some extent, if you do constraint logic programming over a domain of trees and you have both equality and disequality, that gives you Prolog or miniKanren or something like that. I mean, that's very similar to traditional logic programming. So you can look at traditional logic programming as a special instance of constraint logic programming if you look at it that way. Okay. Now at this point, miniKanren has some other bells and whistles, and of course Prolog has lots of extra logical operators and so forth. But if you're just looking at sort of the pure core Prolog, the pure core miniKanren, then constraint logic programming over trees is basically gives you equality and disequality. Okay. All right. So we talked about substitutions, and let's just remind ourselves real quickly of what a substitution might look like. We might have the variable x bound to y, to 5, and we might have y bound to x, for example, right? Or we might even have y bound to a list containing x7 or something like that. Okay, so that would be what a substitution might look like. Now, when I'm showing you this, I'm not showing you exactly how we represent variables. Okay, so here x and y would be logic variables. So how do we want to represent logic variables? We have to have some representation. We could just use regular symbols, like we might in a regular interpreter, but that means then that we have to be a little careful dealing with symbolic data and things like that. There are various implementations of variables we could use. One approach would be to use records. Our 6RS scheme has records built in, and many scheme versions, many scheme implementations had a record system before the our 6RS standard. So we could use records. Records, in some sense, are probably the right way to represent variables. That's not what we did in the reason schemer. Instead, we used vectors. We used vectors to represent variables, and our reasoning for it was the sort of twofold. One is we wanted to make sure that that our code would work in old versions of Scheme that didn't have records. We also didn't want to add all the complexity that comes with records. The R6RS record interface is actually quite complicated. We wanted to keep the code as simple as possible, so focus on the ideas. So we didn't use records. Instead, we used vectors, which means that you can't do unification over vectors in miniKanren. If you do, miniKanren will think that your vectors are logic variables, probably. You can get around that in various ways, but you have to be very careful. So in general, we're just saying, okay, we're not going to care about vectors. No unification over vectors. Now, if you wanted to to add support for vectors as data structures, where you could have a vector containing a logic variable, that kind of thing. There's nothing wrong with that, but you'd have, you'd want to choose a different representation for variables in that case. Okay, so so at this point, if we want to use vectors, I'm going to start at this point going through the microKanren code, right, and start grabbing some of that because let's try to understand how the microKanren code works. You can see that to construct a variable, we just are making a call to vector and scheme. Okay. There's a little more to this. So if I call vector, this is something that will give me back a new vector. This hash in front of this pair of parens, the hash tells you you have a vector. So if I want to have the vector containing 5, 6, 7, I get back hash 5, 6, 7. So that's the representation I'm getting of a vector. I can also play some games here. I can play some equality games. So I can ask if the empty vector is equal to the empty vector, and it is. I can ask with a different definition of equality and scheme whether or not those two are equal. Originally, we had this idea of using the empty vector to represent variables, and I'll have all variables be the empty vector. To my understanding, the quality of the empty vector, whether or not the empty vector is equal to itself, is implementation specific, at least under R5RS scheme. So there's some technical reason that we didn't do it. The other reason is you might want to include something like the variable name. If you're creating a variable that's cool, this variable x, you might want to create vector x. And now when you're debugging your program, you can actually see the substitution that, hey, we have an x there. Okay, so in miniKanren, regular miniKanren, the code you see in something like the reason schema or my gestation, you'll see that we are always creating variables as a vector of one argument. And that argument is a symbol, and that symbol is the name of the variable we're introducing with fresh. So if you had something like fresh x, equal x5, then in miniKanren, basically that fresh is going to make a call to vector of x. Okay, so that's how you'd introduce the new fresh variable. Okay, so the call to vector with something passed in will give you back a new vector, and that's how we represent variables. In microKanren, works a little differently than in miniKanren. We're not passing in a symbol representing a variable name. Instead, passing in a counter, a number. So like vector 0. So it gives a vector of length 1 containing 0, vector 1, and so forth. And we're going to use this counter, just going to increment this counter, and this will always give us a new vector. And this issue about whether or not to pass in a counter versus a variable name and all that sort of thing, it can actually get pretty subtle. The argument for the counter. Okay, so another way. Okay, so let me take a step back. One thing we want to do in microKanren, or that Dan and Jason, or Jason and Dan wanted to do with microKanren, was to remove all of the syntax, remove all the macros, remove things like fresh. So first of all, I'm not sure they always had a symbolic name in order to add to the vector. Probably not. But also, they're just trying to keep the ideas as simple as possible. So having a number where you just increment the counter and use the counter to compare the variable equality, that makes it very simple for variable comparison. If I gave you, there's another reason. If I created two vectors, with quote x, then so let's say I'm going to define variable 1 to be vector quote x, okay, and define variable 2 to be vector quote x. Okay, so first of all, from a debugging standpoint, those look the same. If I ask if they're equal question mark, v1 and v2, yes, because according to Scheme's notion of equal question mark, it's trying to see if they're structurally equal, and they do have the same structure. Both vectors both have length 1. They both contain the symbol x. I can ask another notion of equality, EQV, or EQ, question mark, which is pointer equality. I'm asking, are these two objects, v1 and v2, literally the same vector? Are they literally the same object in memory? They point to the same location in memory. And the answer there is no, because we constructed the vectors at different times. So each vector has its own location in memory. But in order to tell v1 and v2 apart, we basically had to rely on pointer equality. Okay, so that's from a mathematical standpoint, from a purity standpoint. If you're a Haskell programmer, this is considered a side effect. Anytime you're depending on where in the computer's memory an object's been allocated, that's a lower level detail. So the reason to use a counter is to try to get around that equality comparison. Now we can just compare the numbers that are in the vectors. So if I have, obviously if I have vector 3 being, or variable v3 being a vector with counter 0 and v4 being a vector with counter 1, then I can just look at the vectors as they're printed out. As a human, I can tell these are different variables. And the other thing is that if I want to do an equality test, then if I do equal question mark of v3, v4, they're not equal because the contents of those vectors are different. The other thing I could do is I could obviously take, like the car, or sorry, I do a vector ref, not a car. So vector ref, and I just forget the argument order, but yeah. And same thing for v4. So I can reference the first element in each of those vectors, and I'll see that I have a 0 in one case and a 1 in the other case, and that way I could do, I could do a comparison, a numeric comparison, for example, on those two vectors' contents, and they aren't the same because those numbers are different. So it gives me a more pure way, sort of a more mathematically pure way of comparing equality of vectors. Okay, so that's another argument for using numbers inside of the variables. Now, of course, the trade-off is that if your original variable was x in your program and you had x and y, now they're going to show up as 0 and 1. So as a human, that might be a little trickier to map those values. The other issue you have to consider is if you're going to use this counter approach, then you need some way of incrementing the counter. Okay, so if you have 0 as the first counter value, and then you want to increment by 1 to get 1 and 2 and 3, 4, so forth, how are you going to actually increment the counter? Well, one thing you could do is have a global counter, right? So I could define, C to be 0, and then I could set bang C to be C plus 1, and just keep repeating that operator, that operation, and now I get new counter values that I can use. Now, of course, the downside to this, if you're a Haskell programmer, let's say, is that this is a global side effect. It's a destructive update, and it can cause well, depending on to what extent you want to take your purity, this is either like a horrible, nasty thing that should be avoided at all costs, or it's a harmless side effect that's not hurting anyone. I think of this particular side effect as a harmless side effect that's not really hurting anyone in general. It is true once you start getting into multi-threaded code and things like that, then maybe it's not quite so harmless. But anyway, the other debate, besides whether or not you want to have, say, symbols in your vectors representing variables or numbers, is that once you decide on numbers, like a counter, then you have to decide how you're going to update the counter. Instead of having a global counter that gets updated destructively by using setbang, let's say, what miniKanren does is it actually passes around a counter throughout the whole program. So every call to equal, for example, after there's a call to equal, like if there's an equal x5 or something like that, okay, this call to equal is going to return a procedure. Well, if I load miniKanren, it'll return a procedure, and that procedure is going to expect an argument that has the substitution in it, so it can actually perform the underlying unification. But now it's also going to expect an argument that has a counter in it. And that would be especially important if we had an operator that's going to do something like bump up the counter by introducing a new variable. But in any case, now we have to feed through the whole program a counter and increment that whenever we introduce a new variable. So it complicates our implementation a little bit. It's not terribly complicated, but it's something we have to take care of. It does also seem to slow down the system a little bit, having to keep track of the variables. But if you're familiar with the monadic style programming, and if you've done any Haskell, for example, then basically the counter is being threaded through your program monadically. You can think of it that way. And I'm sure there's probably like a counter monad or something like that people use. I mean, maybe it's the form of the state monad. I guess it is a form of the state monad. So we have a substitution flowing through the system, and we also have a counter flowing through the system in microKanren, and we'll see that. Okay, but in any case, that's how we're representing variables. We're going to have in microKanren, the constructor for a variable is going to take C, which is a counter, and it's just going to return a vector containing that counter. In case you're not familiar with the syntax, this is equivalent to define var to be lambda c, vector c. So this var c thing, that just means that you have a lambda. You have a lambda that has one argument in this case. So it's just suppressing the lambda to make it shorter. Okay. So that's var. That's how we construct a var. And once I have that loaded, then I can just do var 0, and we get back a vector 0, var 1, and so forth. Okay. So that's how we construct a variable. So if we wanted to build up a substitution, so we go back to the substitution right here. So let's actually show you what a real substitution looks like. We can introduce the x and y as calls to var. So var 0, and I'll say let y be var 1. Okay, and now we can return that substitution. So let's go ahead and evaluate that expression. And you can see that the variables are indeed vectors that have numbers inside of them. Okay, so that's what a microKanren substitution is going to look like. Okay. So we have two variables that represents our x and y, and then these are the values they're bound to. The other thing you might notice is that there's no dot in this case, in the last one. That's just the scheme printer printing things out in a little more compressed form. It's really equivalent to this. Okay. Okay, so that's really what a substitution looks like in microKanren. And the substitutions, what we're going to be passing around throughout the system, along with a counter, and the point of the counter is so we can create new variables and then increment the counter and then pass that new counter value along. Okay, so Orchid asks, what about gensim instead of vectors? Okay, I realize why it's wrong. And we also could play gensim games, there's no doubt about that. The downside, I guess there are two downsides of gensim. First of all, there's going to be no obvious connection to the initial variables, and that is, I think, a problem with using these numbers as well. But the other problem is that once again, it's sort of this global side effect, right? So, you could certainly do it, but if you want to be sort of mathematically pure, then the way you implement gensim is by passing around a counter or something like that. Okay, so that's one way to do gensim, is to pass around a counter phonetically. Okay, so that's what a substitution looks like. That's what our variables look like. Okay, and if we go back to the microKanren code. Okay, so let's look at the microKanren code here when it comes to vectors. All right, so this is the code to create a vector, right? So just var takes a counter, returns a new vector containing that counter. Okay, so that's the constructor. And then we can also ask if an object is a variable. Okay. So in microKanren, if anything's a vector, we're saying yes, that is indeed a variable. Now, if we wanted to be a little more precise about it, we could do something like this. If I were trying to be a little more software engineering-y about it, program defensively, I would probably do something like an AND of, first of all, is X a vector? Yes. Secondly, is the vector length equal to 1? And thirdly, you could ask, number question mark of, vector ref of x0, something like that, right? So you could even check to make sure it's a non-negative integer or something like that, right? So if you really wanted to try to make sure you had an honest-to-goodness vector or a variable created by the system, then you could do a test like that. Okay, but we're not going to bother about that. We're just going to assume any vector in a system really is representing a variable. And then the last vector operation, or the last variable operation we need, is var equal question mark. This is just going to tell if two variables are the same. Okay, so here's the microKanren version of it, and I'll rewrite it kind of the way syntax I like, the explicit lambda. They're both equivalent. I just like seeing the lambdas. Okay, so var equal question mark, this is an equality predicate, but it only works on variables. So you have to make sure both x1 and x2 are variables, otherwise you could get an error when calling var equal question mark. Okay, and all this is going to do is what I showed you before in the REPL is it's just going to check to see if the vectors, if the first element in each vector, if those two vectors, if the first element is equal. And so this equal also assumes you have a number. So this is only going to work if x1 and x2 are vectors of at least length 1 whose contents are numbers. Otherwise you get an error. So according to this interface, it's going to be your responsibility before calling var equal question mark to verify that x1 and x2 really are vars by calling var question mark on them. Okay, so that's the interface. We can construct a new vector. We can test to see if something's a vector. A variable. And remember, these are really logic variables, right? And then this last operator is going to compare two logic variables for equality. Okay, so those are three operators. I'll go ahead and move the microKanren one up. Okay, and that's it. So now we know what a variable looks like in our system, and that's the first three. Those are the first three definitions in the miniKanren code in Jason's repository. Okay, and that repo, I'll go ahead and move that link down, but this is the repo. So this is just Jason's repo to the code from the original miniKanren paper in the Scheme Workshop. Okay, so those are the variable constructors, variable test, and variable quality predicates. So that gives us the first part of the miniKanren code. The second part of the miniKanren code we already have seen. That's walk. This lets us walk some term, usually a variable, but not always, some term u in a substitution, and lets us know what is bound to u if u is a variable. If u isn't a variable, walk just returns whatever u is. Okay, so this is just one of the definitions of walk we have. This is equivalent to the other definitions. I think the use of this ASP thing is to try to keep everything short, and you can tell, you can see that that we're using our variable interface here, right? So first of all, we're checking to see if u is a variable, and secondly, we are using variable quality on u and v if u is a variable. Let's see. Oh yeah, okay, so we're making an assumption here. So if we know u is a variable, we still need to know v is a variable in order for this to work, right? For the var equal to not give us an error. But we know this because in a substitution, the left-hand sides of the pairs in a substitution, those are always logic variables. So this use of var equal question mark is safe because ASP is going to map over. It's sort of like an ASCII or so it's just going to map over an association list looking at the left-hand sides of those pairs. Okay, and if we find a variable that is the same, has the same counter value as the variable we're looking for, well then we found it in the substitution. And so we're familiar with walk, we've already looked at that, we're familiar with the var stuff. XDES we're also familiar with. XDES is the extend substitution, and that's when we're going to extend the substitution S with a binding between X and V. In this case, X is going to have to be a logic variable, V may or may not be a logic variable. It could be any value that's legal. Okay, so we now understand the first part of the miniKanren code. Or, well, I don't know if we understand it, we've certainly covered it. Okay, we've covered it down to this point. Hopefully you understand it, but certainly we've talked about all of the issues involved. I guess before we go any further, any questions about that miniKanren code before we move on? No, everyone's cool with that? Okay. All right. So let's see if there's anything else. Okay, well, there is another piece of code that we're familiar with. Actually, we're familiar with Unify. So let me move that up there also. Okay, so Unify we've already talked about in great depth. Unifying terms U and V in current substitution S. Right, we talked about that in great detail. And so we could see our friend walk used. We're walking both U and V in the current substitution. We could see uses of the var question mark, right? And we can also see if both U and V are variables, or the walk values of U and V are variables, then we can do a variable quality test using var equal question mark. Okay. If you look at the Unify in the the miniKanren code, you'll notice that we have an EQ test for pointer equality, and that test captures the variable when they're both variables. So that's one bit of difference in the unifier. It's like, we're playing a little faster and looser in the miniKanren code, if you will. We're being more schemely, I'd put it that way. Being more schemely, we're not worrying quite as much about the fact that we're using pointer equality. So that code would be, slightly. If you ported that code to Haskell, for example, you would have to do something like this counter trick. Okay, so actually, I don't know exactly all the tricks you would use in Haskell to simulate the pointer equality, but certainly having a counter that for each variable that you could compare would be one easy standard way to do it. Okay, so at least the Haskell programmers who I've talked to have said that they didn't think the pointer equality in Scheme was a big deal because it's trivial to port to Haskell, but other people might have different opinions. Okay, so we have unify also. All right, let's see if there are any other definitions. I don't think so. I think we've got our definitions now. Okay. All right. Well, let's look then at these three definitions, which go together in some sense. They go together. These are the definitions. The first definition, equal, is the definition of the goal constructor in miniKanren that we're going to end up using to actually use unification. So let's take a look at that. Let's take a look at these three things. Okay. All right. So first of all, I'm going to rewrite this goal constructor in the way I like to do it syntactically. All right. One reason I like rewriting it this way is that you can easily see the nestings of the lambdas. So you can immediately tell that equal is a function of two arguments that's going to return a function of one argument. Okay, so this higher order is a function that's going to return a function. The one argument that it's going to return is this s/c. That's just a convention. There's nothing in Scheme that says that a variable name has a slash in it is something special. It's a convention to show that this single variable is actually representing sort of two values. We could also have just broken that into two values. I think it's a sort of programmer decision as to whether or not it's nicer to have two explicit arguments or to have one compound argument. But the idea of equal is that when we're making a call in miniKanren to say equal 5, or equal x5, okay, so in this case x and 5 would be the u and v coming into the call, right? So the x would be the u and the 5 would be the v in this case, and we would get back a new procedure. So if you try this in miniKanren, if you try loading miniKanren and then just doing something like equal 5, let's say, then you will get back, if you do equal 5, you'll get back a procedure. Okay, and that procedure you're getting back is the result of this lambda. So we're delaying evaluation of the body of this lambda. So this unification that's going to happen doesn't happen until later. We're not actually unifying 5 and 5 right away, or 5 and x, or whatever, x and 5. And the reason we're not unifying x and 5 right away is that we don't know which substitution to unify them in, right? So if we unify x and 5 in a substitution where x is already 6, then this unification should fail. If we unify x and 5 in a substitution where x is bound to 5, then the unification should succeed. Or if we unify x and 5 in a substitution where x doesn't have any association, then the unification should succeed, and it should add a binding for x to 5 to the substitution. So we actually don't know whether or not equal x5 succeeds or fails because we need to know the substitution. in which to unify these. Okay, so that's why we have to wait. That's why we need to delay the evaluation of the unify call until we get a substitution. And that's what the S is. S equals substitution. S is the substitution we're going to unify with respect to. Now, if you look at the regular miniKanren definition, not the microKanren, you're going to see something more like this. It's going to have just an S, or it might even call it an A. More modern versions will have a C for constraint store, but in the older versions of miniKanren, you'll see like an S. If you see an A in the old version, it just also means the substitution. But the S is just the substitution passed in so that we can actually perform the unification, that's all. So here in the microKanren, we have both a substitution and a C, and you could probably guess what the C is already based on our discussion of vars. The C is a counter. Okay, so the C is going to start out 0 at the beginning of the program and then gets incremented by 1. Okay, so if we go back to the substitution we were looking at before, this is sort of substitution. So if that is our S, and our counter is, say, I don't know, well, we already have X and Y, so if those are the only variables that we've created, then our counter would have incremented twice from 0, so now our counter will be 2. So then the S/C is going to look like a pair, a dotted pair. We've basically cons the S onto C, so S/C is going to look like this. So the first part, the car of the S/C is going to be a substitution, and then the coulter of the S/C is going to be the counter. Okay, so that's what the S/C part is. And the U and V are just the two terms that we want to unify. Okay, so that's what that junk is up at the top. All right, so now once we have the substitution, we can actually perform the unification. Okay, so what we're going to do is we're going to unify the two terms with respect to the substitution. So we want to unify. Remember, unify takes 3 arguments. It takes the two terms, and it takes a substitution S. If we look at our definitions of unify, we can see we have a U, V, and S. Okay, so we better feed in an S to are called a unify. Well, the only problem is that we don't have an S. We have an S/C. But we can get the S by just taking the car of this. Okay. Now, if we wanted to make this a little more readable, microKanren might suffer a little bit from being very short. Sometimes maybe it's a little shorter than it could be. If we wanted to make it more explicit, we could do something like this. We could let S be the car of S/C, and we can make C be the coulter of S/C, and that should make things a little more obvious. So here I can say that's the counter. Okay, and now when I'm going to do the unification, I really can just feed in S because that's the name I gave it, the car of it. And it might be a little easier to read. And now, once the unification is finished, I can see what I got back. The name S here is a little misleading. That's probably like an S/#f or something. This is like a maybe value in Haskell, right? So we'll either get back a substitution or we'll get back something saying that we failed, which would be #f in case of unify. So that's what this test is about. If the unification failed, then S will actually be #f, a false value, and we'll ask if #f, which will fail, and then we're going to return M0, which is our real representation of failure, and that turns out to be just the empty list. So unification has a different notion of failure, a different representation of failure than does equal. Unify returns #f if it fails. Equal returns this M0 character, which is the empty list. And we'll talk in a minute about why that is, why it's returning a different value. But that turns out to be useful. Basically, you can think of it as, in miniKanren, we're concerned with lists or streams of answers, not just one answer. And the empty list, or the empty stream, represents that we don't have any values at all to return. So that's really what's happening there. Unify doesn't know anything about miniKanren or the fact that it's running in a logic programming. The notion of unification is far broader than just in logic programming. So unification is sort of this fundamental operator that pops up all the place in computer science. So that's why we're trying very carefully to make a distinction between what unify does as a mathematical operator and what equal does as a logic programming operator. So equal is concerned with returning a stream of answers or a list of answers, whereas unify is just returning either substitution or hashf. Okay, Igor is asking, how to replace failure by a list of successes. That's right. This is a classic paper that talks about how to do this. I will add a link to. If anyone's got the URL for that, I will also add that. But anyway, so that's really what's going on with equal, right? So if we look at equal, we can see first of all we're getting two terms that we want to unify, but then we have to wait until we actually get the substitution. And in microKanren we get a counter also with the substitution, but that's sort of irrelevant from the standpoint of equal. Whether or not we have a counter or not, that doesn't affect them. But we need the substitution, or we need a constraint store. Last time we looked at a constraint store that might have a substitution and constraints for disequality constraints all bundled up. If that were the case, if we had a constraint store, which also we might call C, which might be confusing, but C is a constraint store, then we would probably do something similar, right? We would pull out the substitution from the constraint store. We try unifying U and V with respect to the substitution. We get back some answer, which is either hashf for failure or some new substitution, maybe extended. If the unify failed, then we're going to return M0, which is basically the empty list or empty stream, saying we have no answers. There are no results from this computation. If, however, unification succeeded, and we get back a new substitution, either extended substitution or the old substitution, now we're going to return a value that represents a new S/C. Okay, so we took an S/C, and now we're going to return an S/C. That's why we're building up a pair of S and C. It's a little trickier than that, though, because remember, now we're talking about returning lists or streams, or really streams of answers. Because once we have cond in our language, we can get more than one answer back, right? Once we have disjunction, we can get more than one answer. So instead of just returning the pair, the S/C updated pair, we're actually going to wrap a call to unit around it. And unit in this case is also kind of boring. I mean, M0 is just going to be the empty list we're going to see, and unit is basically just going to give back the pair. And the reason that we were making a distinction, this is sort of a mathematical thing, or a way to kind of keep track of the sort of the monads that are running around inside of miniKanren. So if you're a Haskell programmer, or if you know about monads, the M0 and the unit might look familiar. This is sort of a monadic underpinnings of miniKanren, if you will. But you don't really have to think of it that way. You can just think of unit as returning sort of a singleton stream or a singleton list, okay? And M0 returning the empty list. So really in miniKanren, all these goal constructors like equal, cond, fresh, what they're really going to return are streams of answers. And that stream could be empty, like M0, or the stream could have a singleton element. It could just have one element in the stream. There's only one answer to your computation. Is in a unit, or you could build up longer streams that have multiple answers, or maybe even infinitely many answers, unbounded number of answers. Okay, so the unit and the M0 really is about sort of entering the stream land where we want to turn a single answer we have or no answer into a stream that represents how many answers we have. Okay. Let's see. Got a PDF link from Uncourse. Thank you. All right, so if you're interested in this, paper by Phil Wadler, take a look at that. Thank you. Okay, so that's what equal does. So equal is sort of a wrapper. It's the interface, sort of run as the interface between miniKanren and the underlying host language like Scheme. In some sense, equal is the interface between Unify, which is this mathematical notion. It's this interface between Unify and the rest of miniKanren. Okay, so it's sort of like we're wrapping up. We have this beautiful mathematical operator Unify, and we can't change what Unify does, right? I mean, logicians decided what Unify did a long time ago. You could look up Alan Robinson's papers from 1965 or whatever for that one, but so that we're not allowed to touch Unify. Okay, Unify is like this mathematical logical operator. We can't mess with it. But what we can do is say, okay, well, when we get an answer back from Unify, we can then kind of wrap it up in whatever objects we need, or whatever other interface we need in order for the rest of miniKanren to use the answer we get back from Unify. In that case, it means we want to take the answer and turn it into a representation of streams, either the empty stream or a singleton stream. Okay, so that's what unit and M0 are doing. And of course, if we were in Haskell or a language like that, we'd probably have like a maybe type, I guess, for the substitution thing. And then the rest of this let binding is just pulling apart, the S/C value that gets passed around to get to separate the substitution from the counter. Okay, and once again, the actual microKanren code is a little bit shorter. Okay, so there's it's just taking explicit cars and cutters, but that's basically what's going on. It's nothing particularly complicated. So if we go back to the code now, okay, so we have equal. We can move that up. Okay, so this is the code we've looked at so far, and then actually we're probably most of the way done now with the microKanren implementation. Okay, so let's look at the M0 and the unit. So M0, like I said, it's just returning the empty list, right? So this is representing metaphorically the empty stream of answers. There are no answers to be had. And then here's our definition of unit. Now this definition of unit, I think, is a little different from what it is in miniKanren. miniKanren's unit definition really is like basically the identity function. It's not messing with it at all. But here we're actually consing on. We're building up a pair of the S/C and M0. And M0 is going to be the empty list. So it's like we're consing S/C onto the empty list. So basically we're wrapping an extra pair of parens around the S/C. And we're going to use that to distinguish between the empty stream and the unit or singleton stream. So let's see here. If we got back an S/C that looked like this, if we called unit on S/C, this S/C, then that would be the same as consing this S/C onto M0, where M0 is itself the empty list. So we would just be wrapping an extra pair of parens around the S/C, and we would get back this thing. Okay. So that's all M0 and unit are doing. It's nothing particularly interesting. It's just a way for us to keep track of the difference between a singleton value and no values at all. All right. Is that making sense to everyone? Okay, any questions so far? I know some of you have already implemented miniKanren or microKanren, so that's not surprising that you're following it. But if you haven't seen this before, there are a fair number of moving parts, but they're not that complicated. I think it's complicated sort of the first time, but what I'm really trying to do is not make sure you understand every single piece of code, although hopefully that's the case. But what I'm really trying to make sure is that you could go back and read the microKanren paper and understand what the microKanren paper is talking about. Okay, so you should have a roadmap to all the code at least. There's so much Haskell, Orca says. Yes, there is. In fact, the arguably the first really modern version of the miniKanren implementation was the one done in Haskell. So Amr, Sabri, and Kenshan, and Olekasyov. I think it was the three of them working together, and they Haskellized the code that Oleg and Dan and I had worked on. So there's a whole long history. We have to get Dan on here to tell the whole history. There was Kanren before. There was miniKanren, and Dan did a miniKanren, and then I tried to help him clean that up, and I think Oleg helped him clean that up too. But then at some point there ended up being a Haskell version, and that's the monads. I think the monads became more clear from Haskellizing it. So anyway, so what do we have left? We don't have that much of the language left. Okay, now obviously there are the macros that you could add to to give you a nice syntax for fresh, for example, or cand. Okay, microKanren. The idea of microKanren is we're going to implement this core language, and then we could put the macros on top. So right now we're just looking at the macroless version of the language. We can look at the macros afterwards. But what do we have? Well, we have the call/fresh, and we were talking about before how you could use a lambda and scheme to do the binding, or a function call in scheme to bind a variable, a logic variable to a lexical variable in scheme. That's what call/fresh does. So this is trying to get away from any macros or anything like that. So we'll look at that. And then we have disjunction and conjunction, which are the basis for cand would be like the disjunction, and conjunction would be the body of a fresh, and miniKanren is doing a conjunction or an and. So this is like or and we can see that they have helpers m plus and bind, and these are really stream operators. So it's like m plus, for example, is you can think of it as stream append. We're appending two streams. It looks a lot like list append, actually. It looks a lot like list append. But here we're appending two streams together. So the disjunction and conjunction, this is really about taking streams of answers, like the singleton stream or the empty stream we might get back from equal, and then manipulating those streams in some way to either act like conjunction or disjunction or conjunction. On the call with fresh, its only job is to introduce a new logic variable into scope, so that we can do something like the equivalent of a fresh x and then have a new logic variable bound to the scheme lexical variable x. So that's what call with fresh does. So that's it. That's all we have left. Introducing a new fresh variable and or. Okay, and or are basically built on top of these stream manipulations, which look very much like list manipulations. They're almost exactly the same code as list manipulations, like append. So m plus, these dollar signs. These dollar signs just mean that we have streams. That's just a convention. But if you comment out the procedure line to this code, this looks pretty close actually to the definition of append. It's almost exactly append, really. we could change m plus to append, and basically we end up with append. Okay, so this m plus is basically append, just append over streams, and bind is another Lispy operator called mapcan from old Lisp. We're doing a type of mapping operator. And there are a couple different ways to define bind in particular, but m plus and bind also are very monadic operators, so if you're familiar with Haskell or monads or whatever, these also might seem familiar. Okay, so let's see. If $1 is infinite, it would never reach $2. Is that a problem? Are you talking about m plus, or are you talking about bind? M plus. Okay, yes. So you're getting at kind of the core of things, which is so the search strategy that underlies miniKanren. It's really the m plus and bind that control the search strategy. Okay, and whether or not you want to have a depth first search like you have in Prolog, or an interleaving depth first, or an interleaving search like you do in miniKanren, that's going to depend on some of the tricks you play in m plus and bind. And the microKanren paper, for example, talks about this. It shows you a couple different definitions and shows what some of the trade-offs are. And we might even want to look at some of those other definitions, like how do you get depth first search and that sort of thing. But you're right. If we have two streams, 1 and 2, and the first stream is infinite, we have to be careful, because if we only look at or consume values from the first stream, we'll never see any values from the second stream, and that will give us like depth first search. That's what you get in Prolog. So it turns out that you have to be a little careful with how you implement that part of the search. Absolutely. So we will we'll talk about that too. Okay, so let's first look at the call with fresh before we get into the stream manipulations. Yeah, and once again, what we were looking at a couple weeks ago was this notion of fresh. The idea that fresh var x g1, that we can actually turn these fresh calls into basically procedure applications. So, for example, I guess the code we really have is something like this. If in miniKanren we had something like fresh xy equal x5 equal y6, then that would be very similar, right, to this sort of code, right? So we're making new logic variables. Actually, I'll just bring this code down. We can actually try to make it microKanren now. So we already know how to make a logic variable. Make a logic variable by calling var and feeding in a counter. Okay. So var 0 is going to give us a new logic variable. Var 1 will give us a new logic variable, and these logic variables will be distinct from each other. Okay. So this is how we create logic variables with var 0 or var 1. And if we, I guess one way we could look at this code, which would be really equivalent, we could say let x be var 0. So remember, that's going to give us a vector. Var 0 will give us a vector of length 1. And now we have the body there. Okay, so in scheme, let is equivalent to lambda and application. Okay, so this bit of code up here really is the same as this bit of code down below. Okay, so these lets could expand to lambda and application. That's has the same meaning in scheme. So here we're just saying we're giving x a name. This is just a regular scheme variable. This isn't anything special. This is a regular scheme lexical variable. We're saying, okay, let's introduce some variable x that's bound to the vector of length 1. containing 0 that we get back from the var 0 call. And then let's do something similar with y. So in the body of the innermost let, x and y are going to be are now going to be bound to these vectors, which represent logic variables. So then we can have some sort of conjunction, binary conjunction, let's say, and we can call equal equal on x and 5. And we already saw what ends up happening, where we have basically equal equal, that call is going to return a new function that expects to take a substitution and a counter and all that stuff. But anyway, we need to be able to introduce fresh logic variables so we can have the x and y going on. If I really wanted to be sort of pedantic about it, I guess we could look at, maybe we could do something like look at this in greater detail. So what would it be if we had, something like fresh xy equal xy? If that were our miniKanren code, what would it look like? If that were the whole program in miniKanren, if that were wrapped in a run, let's say, what would happen? Well, we would have, metaphorically, some substitution S, which would be the empty substitution to start out with, the empty list. And we would have some counter C, which would start out as 0. And we could have our initial S/C would be cons of S onto C. So that's our substitution and counter pair that we're passing around. And now when we have the fresh xy, that could turn into something like these two lets, where we're saying let x be var 0, let y be var 1. And now we're going to do a unification, or so we're going to call equal equal xy. Remember, that's going to return, equal equal xy will return a procedure that expects an S/C, right? So we could, we could end up calling the procedure we get back from equal equal xy. We could pass in then the S/C that we have, the initial S/C, right? And that's going to give us back a new stream of S/Cs. It could be the empty stream, the M0 stream, it could be singleton stream. But that's basically what this code would be equivalent to. If we really want to be pedantic about it, we could put it like a run queue or whatever, and then we'd also end up introducing a queue variable somewhere. But that's basically what this code would be equivalent to. We're introducing, we have an initial substitution, an initial counter. We have an initial S/C, which is those two cons together. And then we're introducing two variables, x and y, through the fresh. And now we're going to, actually, sorry, the other thing I should have done, actually what that should have been is, that's just going to be the var C, right? Yeah, so we have to get the var C stuff. So so now you can see it's like a little pain to have the S/C together. But if we really wanted to do this right, so we'd have some S/C, which was that, and then so var C, well, that's really var of the the cdr of S/C. That gives us our new C. And then what we would also have to do is let bind C to be, add one of cdr S/C and all this. Like we're going to have to increment the counter and all that, and feed that through. So so that we'll have a new updated counter when we want to do Y. So this sort of stuff. That's what the sort of the assembly language of miniKanren looks like, is these little counter manipulations and introducing a new fresh variable by making a call to var and manipulating these S/C pairs. That's what microKanren kind of looks like when you look at the really low-level underlying code. But that's the idea. Okay? So call with fresh is going to let us do this binding. So here we're using a let binding, but instead of a let binding, we could also do a function call. So instead of let is equivalent to having a lambda, like lambda x, and then passing in an argument that we want to bind. So the call with fresh, so we could do something like call with fresh of some function f. So we could say lambda x equal x5. All right, and the call with fresh is going to create a new variable, and that variable will be passed in to this procedure, and that variable will end up therefore being bound to x. So it's like a kind of a low-level mechanism. It's using schemes lambda, which does binding, for binding of the logic variables. Okay. And then this whole call to fresh call will return a lambda s/c when it's procedure. So anytime you see a lambda f/c, that's a goal. So that's what we call a goal. So a goal is something that takes an s/c and returns a stream of s/c's. That could be an infinite stream, it could be the empty stream, or whatever. But that's what a goal is. A goal, whenever you see is lambda s/c's, that's a goal. And the goal takes an s/c and returns a stream of them. Okay. So we saw our first goal we saw is in the context of equal. And we'd say that equal is a goal constructor because when you call equal, you get back a goal, a function that takes an s/c and returns a stream of s/c. Same with call/fresh. Call/fresh is a goal constructor, but when you call call/fresh, you will get back a goal that's expecting an s/c. Okay. And you can see, because we're going to introduce a fresh logic variable, that first of all we have to get the counter. We need to know what the current counter is so we can pass that counter to var. And as we've already seen, the coulter of an s/c is indeed the counter. And now what happens is we're feeding to f, and remember f is some function like this. We're feeding to f the new variable that we've constructed, and that's the var with the counter. Okay, so we create new variables, so we have some vector with a number in the first position of the vector, and that represents a logic variable, and we feed that logic variable into the procedure we get back from this lambda expression. So we're feeding in to x, or we're binding x to this logic variable so that it can be used in the body of this program. And then from this call to f(c), we're going to get back a goal like this. We'll end up evaluating equal x5. Equals a goal constructor. We'll end up with a goal which expects an s/c. So the result of this call to f(c) really is a goal, and then we need to pass in an s/c to the goal, which is what we're doing here, building it up. Once again, the microKanren code is trying to be very succinct. We can try to make this a little more explicit. So we can say something like let g be this call. So that's our goal. And then we can call the goal with this new s/c. In fact, we can even be a little more explicit than this. We could say let our new s/c be this thing. And this is our new s. Actually, let's just be really explicit about everything. And we have a new c also, which is this. Whoops. Okay, so this is how call/fresh could also be written to be more explicit. So we have a counter that we grab. Actually, I'll go ahead and put the s up there because they don't interact with each other. Okay, so we can tear apart the S/C into separate substitution and counter values. Okay, remember, so this is the substitution. This is S, and this is the counter. And now G is the goal returned by passing a new variable to F. And I guess if we really wanted to make this clear, we could even say, let V will be our variable. And we're going to call F on V. Okay, so we're going to back a new goal. And the new goal is going to expect to be passed an S/C. So we have to build a new S/C. We have to increment the counter. Actually, there are no dependencies between those two, so we can make those at the same level. So we have a new counter. We have the old S. And so now we're going to build up an S/C. And that's really just a cons, but whatever. So we're building up a new cons pair. So we have this new. So we have the old substitution, but the incremented counter here. And then we're going to take this new S/C and pass it into the goal we get back. So in other words, this call to equal x5 would return a goal, would evaluate to a goal, and that's the goal that we're going to pass this new S/C thing. So we're going to increment the counter before we pass it into this the goal we get back from equal x5. So these two pieces of code are the same. I'm just being a lot more explicit in the second one. Any questions about that? Metaphorically, this is very simple. We are just creating a variable, and in order to create the variable, we call our var helper. We have to pass the var helper a counter, which is just a number, 0, 1, 2, 3, or whatever. And we have to increment that counter so that in the future, if we want to create more variables, we can get the new counter. And we package up the substitution and the counter together. So basically, most of this code is tearing apart the S/C, incrementing the counter after we create the variable, right, and then building back up the S/C. Oh yeah, do I want to make? Okay, Daniel, good call. I forgot to make my top level call/fresh explicit. Yeah, so look at it this way. Okay, so call/fresh is a goal constructor. It's a goal constructor because it's a function that, when called, returns a goal. So you can see lambda f part is the goal constructor, and the lambda sc is the goal that it constructs. Okay, and that's what we mean when we talk about equal being a goal constructor, or fresh being a goal constructor. Call/fresh is sort of the demacroized, non-syntactic version of fresh. It does the same job, except it's not doing the conjunction. It's just it only has a single goal as a body. Another thing we can see. Okay, let's just kind of revisit one design decision with the microKanren. What would happen is if instead of passing in S/C as a single argument, what would happen if we passed in S and C as separate arguments? Okay. If that were the case, we wouldn't have to do this work right here because we would already have the substitution in the counter as separate arguments. So that just goes away. Okay, so that code gets simplified. And then here, when we're passing in S and C to G, we don't have to do this consing. That goes away also. Okay. So you can see the code gets a lot shorter. You know, the downside, I think, is that now you have to have like lists basically at some point containing the S and C's for the actual value. Well, let's see. Yeah, because you're always having to return an SC pair. I think the downside is that if you look at equal equal, go back to equal equal. The unit, I don't know if it's downside or not, but unit's going to have to wrap up the S and C. Actually, the way this is abstracted, I think that would be fine. You would just pass in S and C separately, and unit would probably do the job, or you'd have something like unit that would package those up for you. So it might be a little cleaner. I don't know if it messes with the math, with the monad laws or something, but you can see that there's a disadvantage of having S and C come in together as one argument. If you pass them in as separate arguments, it's a little cleaner. One advantage of the S/C approach, especially if you use records, is that if you want to add more fields, like say for example you want to add disequality constraints, okay, so then in addition to a substitution and a counter, you also have disequality constraint information. Then you can just have a single argument which has everything bundled together. Whereas if you want to have separate arguments for everything, then you end up with you have an S, you have a counter, you've got disequality constraints, you have symbolo constraints, you have absento constraints and numero constraints, and this can start finite domain constraints. It can start getting out of hand. So there are other ways you can approach it. Probably the right way to handle it really is just to pass a single record through everything. But you can see the trade-off, some of the trade-offs there between having a single S/C versus having separate arguments. You spend a lot of your time and a lot of the code is breaking this thing apart and then building it back up together. So it might obscure a little bit what's going on. I'm not sure. Maybe a microKanren that passes it separately is better. Different trade-offs. Okay. Yeah, so that's what call with fresh does. Call with fresh is a goal constructor, so it's a function that produces a function that takes an S/C. Its job is basically to create a new logic variable that's going to push in. That's going to pass into the function f. Okay, and as part of this, it has to increment the counter. So if you want to nest call/freshes, for example, or have another call/fresh in your program later on, that the counter will be incremented properly. All right, Nahal has a question. Curious to understand more about the pros and cons of a monadic style on one hand, mbind, mplus, etc., and using success and fail continuations on the other. Some level they must be equivalent, for example, a Wadler paper or Oleg's Haskell version versus the miniKanren from recent schemer. But as one starts adding new features, like probabilistic programming semantics to the system, perhaps things seem to favor one versus the other. Yeah, so I think one cool thing to do would be, once we finish with the microKanren implementation and maybe the macros on top, to go back and look at the success and failure continuation version of miniKanren. miniKanren originally was written using success and failure continuations instead of streams. And it turns out there's a paper by Dale Valancourt and Mitch Wan showing that for backtracking search, they're equivalent. You can express each other, one in terms of the other. So you can use streams, you can use success or failure continuations. I guess you could use probably single delimited continuation to do all this stuff. For the probKanren, probabilistic logic programming stuff I've been doing with Rob Zinkoff, we've been using a continuation passing version of our code because I thought that was a little easier for the type of control flow. As far as the trade-offs, I don't know. When I run into really complicated control flow, I tend to start with continuations just because they're really flexible. And then as I understand the problem better, I tend to try to get away from the continuations because I think it can be At least I personally find it kind of hard to reason about what a change the continuations will do. Like if you swap one continuation for another one, it seems to get pretty tricky. At least I have trouble keeping in my head. The stream stuff seems easier. So yeah, I guess my general approach is I often start with continuations and then I go to streams. At this point, we have enough, for sort of the standard miniKanren and microKanren, we understand the streams version pretty well, and it's pretty clear how to get depth first search versus interleaving search and things like that, just using streams. But with the prob-Kanren stuff, the control flow changed completely, and I wasn't sure where it was going to go. So it would be nice when we're cleaning up the prob-Kanren to see if we can get a nice stream-based implementation. And I'll talk about prob-Kanren some other time. Maybe Rob will come on. So if you wanted to, just to show you really quickly what it might look like, so if this is the stream version of equal equal, right? And once again, we kind of have this noise of building stuff up with tearing apart the Karen encoder, but really what it comes down to, so the most important thing other than the call to unify is what happens at the end, right? If you get it back as a new substitution, or do you get back hash F representing failure? The way this might work with a continuation passing style, it would look something like this. So SK is the success continuation, FK is the failure continuation. And when we want to fail, instead of invoking M0, we would just call the failure continuation, and it would know what's supposed to happen next. Like, it would initiate effectively the backtracking. When we want to succeed, when we have a value to return, we've succeeded, then we would call the success continuation, and the success continuation, in addition to taking the value, would also take the failure continuation in case we ever needed to backtrack later because of failure. So this is what you would see with the continuation passing version. This is like the two continuation version. And the paper on the equivalence between streams, so that was by Dale. I want to make sure I guess Fallon Court. I'm probably spelling it wrong. And Mitch Wand. And this was on the equivalence between two models of backtracking or something like that. It had like two models of backtracking in the title. If you can find anyone can find the link, I'll put it in there. Yeah, but that paper talks about how continuations, two continuations, and streams are equivalent, or the equivalence between them. Okay, yeah. So you can do these things with continuations instead of streams, and it works out fine. Different trade-offs. Okay, great. Here's the paper. ICFP 2004. Yep. Relating models of backtracking. That's it. Good. Yeah. So that's an interesting paper. Not sure if the talks are online or not, but and VA spelled Dale Valancourt a little wrong. Okay, so it's Mitch Wand and there we go. Okay, so that's the paper. So if you're interested in the connection between backtracking using continuations and using streams, take a look at that paper. Cool stuff. All right. So anyway, we have the call with fresh, and now we know what call with fresh does. Okay, so that's that code is done. Move that up there. And so we're almost done. We've done the bulk of the code. So just kind of recap. So the var interface, this is for creating a variable, asking if something is a variable, checking to see if two variables are the same variable. Walk lets us look at a term, often a variable, find what the term is associated with in a substitution. Okay, this is especially important because we have these triangular substitutions. So looking up a variable in the substitution can be a little more work than just like a member call in an environment. XDES allows us to extend a substitution. It's very simple, just building up a new cons pair on the front of an association list. Unify allows us to unify two different terms with respect to some substitution, and this will return either #f saying the terms can't be unified, they can't be made equal. There's no extension to s that will make them the same term, or it will return a new s, either the same s saying that if we get back the same s from the call to unify, that means u and v are already the same. If we get back an extended substitution s, that means that u and v aren't currently the same, but they could be made the same. They could be made equal. And the extension of the substitution tells you what you would need to substitute, which variables you need to substitute in for u and v in order to make those two terms equal. So that's what unify does. And unify is the heart of the constraint solving in miniKanren and pure, sort of standard miniKanren or logic programming. And this unify is going to, well, one thing that we talked about before is there's no occur check here, right? So in this version of miniKanren, x and list containing x will unify. Okay, so or we could unify x and list containing x. Unify is the heart of equal equal. And then we have equal equal, which is a goal constructor. Right? We can see the lambda s/c that it's being returned, and this will unify two terms u and v, but we don't know what substitution is in effect until later. That's why we have to return this new function. And then once we unify u and v, we do this check to see if s is false. That means that unification failed. Then we're going to return m0 representing the empty stream. Otherwise, we're going to return a unit stream representing a single answer. And that answer consists of a substitution s and the counter. And at the end, we're going to ignore the counter when it's time to print out the answer or return the answers. We don't care about the counter at the end, but we do care about the substitution. The substitution is really telling us the constraints that make the system work or satisfies the system. And then M0 and unit we talked about. Those are these monadic Haskell-y things, if you will. And M0 represents the empty stream in our case, and unit represents the singleton stream. We have one answer. And then we have call with fresh, which is going to let us create a new logic variable and then bind it to a scheme lexical variable and then run the goal inside of f. So f is going to have to be something like lambda x and then some call to a goal constructor like equal equal or another call to fresh, something like that. And sort of the main work that's happening here is that we have to create a new variable using var, feed that variable into f, and the call to f had better return a goal. So f has to be itself a goal constructor. A goal constructor is just any function that returns an lambda s/c. And then we have to pass in an s/c. And so we use our old substitution, but then we bump up the counter to get a new c. So that's it. Now we have everything except for conjunction and disjunction. And in fact, we can even write miniKanren programs now. We don't actually need conjunction and disjunction to write a miniKanren program. We can actually try writing a simple one now. So let's see if we can write a little simple program just using what we have. Let's try this. So let's try doing a very simple query. This is going to be kind of like a run one queue of, or let's say run one x, of equal x5. Okay, this is about the simplest miniKanren program we can imagine. And of course, in miniKanren, this is going to return one answer, right? This is going to just say that, give us the answer 5 back. Okay. So we can try doing an equivalent program now in microKanren. Let's see how we can figure this out. So first of all, the equal x5, that part's still the same. We still have equal as a goal constructor. Run does some extra work. First of all, it's only going to give us one answer back, but it's also going to clean up the resulting answer. We're not going to have something like run right now. We're lower level. So run really, if we didn't have run, metaphorically, what we get back is a substitution saying x is bound to 5, right? So that's what we're really going to see from this system. We're going to see something like x is bound to 5. We do, however, need to introduce some fresh variable x in order for this to work. So we can do a call with fresh, and that's going to create a new variable for us, but to call that variable x, we're going to have to pass in a function, which is going to be like lambda x equal x5. So this function, lambda x equal x5, when that function is invoked with an x, then we're going to end up calling equal x5, which is a goal. Equal equals a goal constructor, so we'll end up with a honest to goodness goal. Okay. So that's our call with fresh. That's how we get our x in scope. But we also need to make sure that we have an s/c, a substitution and a counter, being passed through the system so that it all works. So we need to kind of kick things off. So call/fresh, that's also a goal constructor, right? So this is our goal. So we can look at it this way. So here's our goal. Let g be the call/fresh. And we need to call this goal g and pass in an s/c in order for this to work. Okay. So let's try creating s being the empty substitution, which is the empty list, and trying the counter c being 0. Okay. And now we can say that s/c has to be the s and c together. Okay, so now we have an s/c, substitution and a counter, and we have a goal, which is what we get back from the call/fresh, and now we can call the goal with the s/c. I think this will work. Hopefully it will. I guess we'll find out in a minute. All right, so let's try loading it up again. And, okay. So I think what I want to do is get the microKanren code. All right, so I'm just going to grab this microKanren code, just the parts I think we need. Let's see if this works. Uh-oh. Did I just crash Emacs again? All right, I think I crashed Emacs. See if I can. That's the second time today I've crashed Emacs. I don't know whether or not to feel proud or upset. Let's try it again. Okay, let's load the miniKanren. Okay. All right, let's see if our code works. Yay! It did work. Okay. So notice that what the thing it returned, first of all, it has a counter in it. Okay, so the counter is 1 because we introduced one variable. That's from the call with fresh. So the counter was 0, now it's 1. And also notice that we get a substitution back, right? So this is our substitution, and the variable, the vector containing the number 0, that's the same as our x, really, right? Because that was our first and only variable we've created. So that's the same as saying x equals 5 at the end. Okay, that's really what they're saying. The other thing to notice is there's an extra set of parens wrapped around this s/c. So, you know, the s/c is this thing, but this is really a unit of the s/c. That's that extra pair of parens wrapped around, because remember, a call to unit is going to cons the s/c onto the empty list. So that's it. Yay, it worked. Great. Okay, cool. Yeah, so you can see we already can run miniKanren programs now, right? And if we could change this program a little bit, let's try doing a unification that doesn't succeed. We could. Let's see. Oh, actually, okay, we can show. Oh, yeah, we can show a good, interesting example. So here's an interesting example. This is actually a pretty interesting example. Let's see what we get back from this one. If you've noticed, I've done something sneaky. I'm now unifying x with a list containing x. Okay, and that's supposed to be illegal according to the rules for unification. But if I run it, instead of failing, sure enough, it gives us back the substitution, and we can see this substitution, which really, if you put the dots there, it really looks like that. Okay, so we can see we have self-reference. We have the variable 0 referencing a list of length 1 that contains the variable 0. So that so Orchid was worried as loop. If we try to print out, if we try looking up using what's called a walk star, which is a deep walk. If we try looking up the value of x in the substitution using a deep walk, then, yeah, if we're not careful, if we don't determine that we have a circularity, then it will loop forever. So it's because we're not reifying the answer, trying to make it in a nice way, print it out in a nice way, that we can get away with this. Okay. If we wanted to reify the answer, we'd have to be more careful. But anyway, so we're being a little naughty here. Because we don't have a recurse check in unification. Let's see if we can do another example, one where we fail. So let's just, instead of the call with fresh, let's just try doing unifying 5 with 6, let's say. See what happens there. Sure enough, we get back the empty list. And remember, that's the same as M0. So that's, whoops, that's like M0, that's the empty string. Yeah, okay. All right, so we actually can do some miniKanrening now. The big restriction is we don't have conjunction or disjunction, right? The only thing we can do is have a single call to equal. So that's not a very interesting. It's not a very interesting logic programming. I mean, we actually can do sort of surprising amount with a single call to equal because we're allowed to have arbitrary terms. Let's say we wanted to do something like fresh x y equal x5 equal y6, and then equal xy, right? I mean, it looks like that's got a conjunction in it, but if we're a little bit clever, we actually can express this sort of thing. So first of all, we need more than one call with fresh. So we have the lambda x introducing the x variable, but we'll also need another call with fresh, and this one will have to introduce the y variable. Okay, so if we just wanted to, let's say, unify x with y, we could do that. Okay, and that should let us unify x with y. Let's try that, make sure that works. Yep, that works. And we can see our counter is bumped up to 2 in this case. But now if we actually want to do something like unifying x with 5 and y with 6, right? So if we want to unify x with 5 and unify y with 6, and then x with y, well, that's a problem because that's a conjunction, and that's not gonna work. Call with fresh doesn't know about conjunction. What will actually happen, and this is a common source of error in miniKanren, scheme doesn't know about miniKanren. So this lambda has an implicit begin in it. This is really the same as begin of those three. Okay. And what will happen according to scheme semantics is that it will evaluate this expression, then ignore it, evaluate this expression, then ignore it, and then evaluate the last one, and then give us the answer of that. Okay, so it's going to basically evaluate this equal x5. That will evaluate to a procedure, which is a goal, but then it will be ignored. So I believe this will actually give us the same answer as before. Let's see. Yep, sure does. Okay, so we can't just have a bunch of calls to equal and inside of this lambda y and have that work. So that's not good. I'll leave it here because it's actually kind of interesting. So we have to be a little more clever. But it's not really that hard because what we can do is have a call to equal that looks like this. We have the two terms that we want to unify. And we say x we want to unify with 5, y we want to unify with 6, and x we want to unify with y. Right? So we could do all of them at the same time, and that I expect would fail, right? So let's see if that works. Yep, that fails. Then we can do a more, let's do a similar example, but maybe it's a little more interesting. Let's try, we go back to our original code. How about we do the equivalent of x, y. How about we do, I don't know, what's interesting? How about x, y, z, and we unify z with the pair, or with the list x, y. How about we do that, okay? And so now we're going to need, obviously, another call with fresh. And we'll have a lambda z. And now we'll do something similar, except in the last place we'll have z. And then here we're going to have x, y together. All right, let's see if this works. Okay. So let's see. So first of all, the substitution is this part. The counter is 3. And we've got 3 different bindings here. We can actually tell which one's X, which one's Y, and which one's Z just from the counter, right? Because so the X is getting introduced first, so that's here we have X equals 5, and then Y gets introduced second. That's Y equals 6. You can see that, and then Z is equal to, once again, scheme suppressing the dot, but there's actually a dot there, and then this is the list. So 0 is X and 1 is Y. So sure enough, we got what we expected. Okay, so we already have enough power to express a bunch of unifications that are together. Okay. Okay. So we actually have a working miniKanren core. We don't have conjunction or disjunction, and as we can see, we don't have much code left actually. There's not much left. Just a couple definitions, and I've already said that M+ is basically append, like a fancy version of append. Bind also isn't super special, so we don't have much left. We can already see this lambda SC that tells us that dish is a goal constructor and conj is a goal constructor. Okay. But in order to really do these two sort of credit and to talk about how you might change the dish and the j, the conj to get different search behavior, I think we should probably wait until next time to talk about that. And yeah, so why don't we wait until next Sunday to talk about sort of how the streams work and the interleaving and how the search works, and that's its own sort of interesting topic. But we've covered all of the things involving variables, substitutions, looking up a value in a substitution, unification, introducing a fresh variable. All those things we now know. So the only thing we have left now is what to do with the streams when we get back answers from an equal call or whatever, or if you have a cond equivalent of cond and now you have multiple answers back, how do you combine those in different ways and so forth. So everything left is search related, metaphorically. And we might even talk about the continuation approach to backtracking or something like that. But I think we should hold that off for next time. So are there any questions about that? Any of the things I covered? No questions? Okay, well, makes sense. Okay, well, hopefully that's clear enough that at a minimum you can go back and look at the miniKanren paper. I mean, if you already implemented miniKanren or microKanren, I think probably you know most of the stuff already. But if you haven't read the microKanren paper, you should now know enough where you can go back and read it and understand what's going on. If probably could have understood it anyway, but I think at this point everything should be kind of clear where things lie. So everything except for the search mechanism, which as you can see isn't very long, should already be spelled out. So okay, well, cool. Let's see. So we went. We're at 2 hours now. So I think we're probably in the Hangout now, but I know some people are working on things that they would like to show off. So next week, if you want to show anything off, just let me know. And if you don't want to show things off, or you want to do it in private or whatever, that's fine too. Or if you want to show it off on the message board, I'll go ahead and create a message board, and we can, or a mailing list or whatever, we can start communicating about that and ask questions and show off what we're working on and so forth. So yeah, so next time, the stream manipulation and search for miniKanren, and talk a little bit about that. It's not much code, but it's don't be lulled into thinking that doesn't mean that there's a lot going on there. You can manipulate the code. You can change one line of that search code and has huge impacts on performance of miniKanren and whether or not you can go in infinite loops in certain cases and stuff like that. So it's subtle code. Short, but it's subtle. And like I said, you can do this with continuations also, and that's fun to look at. Okay. Well, thank you all for joining the Hangout, and I think a couple more Hangouts, and then hopefully we can start working on projects together and things like that. People already are starting to work on projects, so that's cool. But hopefully this is making clear aspects of the miniKanren implementation and how to use miniKanren and all that. So, okay. All right, well, have a good weekend, everyone, and I will see you next week, and I'm stopping the broadcast.